I'm going to record. Although maybe you guys can turn off your mics because I can hear the like sound. If you, I'm going to.
Yeah.
I just muted you. Okay. It's just for the background noise. Okay. So if anybody does ask a question, like online, if you will, I'm just going to repeat it out loud. Oh. But we need some. So after testing this in 110, it seemed that my handwriting was a lot better when I sat down rather than walking around. We did talk a lot about RC circuits last time, and I hope that was able to make some things clear. And RL circuits, pretty similar, really. Almost like the same thing but opposite, although that's not a... So if I have just a simple RC circuit, and why is it first order? There's only one energy storage element. And just as a review, right, if I have an inductor here, right, I can add these up, right? If I have parallel inductors, right, if I have parallel inductors, I can just add them up. And yeah, I'll give you this is like a kind of a trick question. Now you might think, I see two inductors in between two resistors, so it must be a second order circuit. But when it actually comes down to it, because let's just do a mesh, right? So we'll have, that's our current, right? So we'll just have it all going in the same direction. And so this we'll just call VR1, VL1, VR2, and VL2, right? Well, let's write the mesh equation for that. So VR1 plus VL1 plus VR2 plus VL2 equals 0. We'll see we can rearrange how these things are added, right? And if I use the impedance method where ZL equals SL, right? And that the equation would become I, and I'm going to collect the I's, right? So I times R1 plus SL1 plus R2 plus SL2 would equal 0, right? Well, think about it. Look at this, right? I can combine that into SL1 plus L2, and see, that means it's just first order, right? Now, this will not be on the exam, but just I think by talking about it, you get a better feel for what's going on. So, and I'd like to think, right, you already know. You've had differential equations, you've had your circuits. The time domain equation of a first order circuit like this is going to be exponential to k. All right, now let's find out, first of all, why that is so. All right, let's do a nodal analysis. Let's see how that works for us. All right, so I'm going to call that node 1 plus minus plus minus. All right, so IR plus, so I have to, IR plus IL equals 0. I know it's a little like weird. How can the current be both leaving? But it really just points to the fact that that's how nodal analysis works. You can do that, and then if it doesn't make physical sense, if you properly keep track of the pluses and the minuses, you'll still get a physical solution. All right. So that would be V1 divided by R, right? Now, just like you, I'll forget things. So I kind of will say, all right, what's IC? Because like I'll try to, usually I will end up memorizing one thing and then modify it. So if IC equals C times dV dt, then VL will equal L, sorry, DI dt. All right. Now, I'm just going to rearrange it. That means DI dt equals VL over L. That means I equals the integral. Okay. And which, this is true, but when you're trying to think of things intuitively and answer questions off the top of your head, because in some ways the 101 is like a job interview question, right? So rather than get into that, you might say, maybe nodal analysis isn't the way to go here, right? So I'm going to switch to mesh, right? And yeah, when you see a problem and you're doing a solution and you say, all right, I can muscle through this way, but is it an efficient use of my time? I'm like, no, not necessarily, especially because I really want a differential equation. So I'm going to go back to my nodal, a mesh analysis, right? And get VR plus VL equals 0. VR is still I times R. VL is L di dt equals 0. Di dt equals minus IR divided by L. And this is, and this relationship is essentially why I abandoned this method, right? And that could happen, right? But notice, the thing, technical term, or I'm going to say it. I'm going to use what my Calc 2 teacher said, all right? And in this case, or I'm going to paraphrase because it was Calc 2 and not differential equations, but the derivative of the mess equals the negative of the mess. Now maybe that, so here it is I've got a derivative of I, we can call I the mess, equals I, but there's a minus sign there. There is only one thing, right, that will solve that equation, and that's some kind of exponential decay. All right, and I've looked in my own differential equations book that I had, and they spend a long time showing you all these various manipulations on how to get there. But you've already done this probably for a homework assignment in your differential equations already. So you might forget what's going on, but the derivative of the mess equals, the inverse of the mess. All right. So we know that this is some kind of exponential decay. All right. Now we know that we've got the RL in there, and yeah, from last time, RC circuit at the baseline was e to the minus t RC. Well, how do we have an easy way of remembering this? All right. E to the minus t. And then I'm going to put L question mark R question mark. Well, L is an energy storage element, right? It stores energy. Now, with the RC, it was, I think, maybe easier to think about where we were filling up a bucket and the charge was the water molecules, and as it made the level, that was the potential voltage, the potential, and we stored it through charge. Inductors store energy by electrons moving around in, kind of a circle action, right? So really, if you think about your second order differential equations of a mass spring system, right, you're storing energy one way, and then you're storing it in the spring, you're storing it in movement, you're storing it in a mass moving stores energy, right? So the thing is right, the bigger your storage element, no matter what it's made out of, right, the more energy that will be stored. So the longer it will take to either fill up the element with energy or get that energy out. Well, what will make that happen? E to the t minus L. So the bigger L is, right, the slower this will decay, right? So if I have two exponential decaying things, right, L2, and yep, the units do not match. Yes, I get it. So I'm saying that's L2 and that's L1, and yeah, L2 is going to be greater than L1, right? Because it just scales that way, right? It'll take more to fill up, it'll take more time to get out. Now then, what about R? Now, in the RC circuit, I think that was fairly easy to conceptualize, is that you're filling a bucket, and like the thinner the hose, the higher the resistance and the longer it took. But the RL circuit is in fact different, all right? And it has to do because we're dealing with something that's moving, right? So if I have something moving, right, like the bigger the brake, the faster it will decelerate, right? So that would mean that R would be here. Now I found another analogy is that we can call it the hose analogy. Or it's the water wheel analogy, sorry. So when I'm pumping water, right, current this way, right, if I'm going through a membrane here, it's a resistance, okay? So this is just like a flywheel, right, that it can store the energy, but it moves very easily. So if nothing is moving and I turn on this pump, it's a lot easier to spin this up than to go through the resistance. And in fact, after a long time, right, or I mean, it starts at 0, and eventually this, before this is spinning, there's some mass and there's a resistance to get it spinning, right? So the current will be going through all the way through the resistor, right? But then as this starts to go, it gets easier and easier to keep it going to the point where all the water goes through here, right? So in this particular case, the water flow, or IL, is going to increase up to some constant value. And the resistance after a long time, there'll be no resistance to the water keeping that spinning, and so no resistance compared to some resistance, right? So the thing is the bigger this is, the more it's going to want to go through here. So if I have R1 and R2, in this case R1 is bigger than R2, all right? And the bigger this is, the longer it'll take, because there's more mass to get it up to speed. So, and then if I turn the pump off, right, the bigger the resistance is here, the faster it's going to stop. It's just like putting the brake on. I take the external, I stop pedaling, I take the brake off, and so it'll decay faster too. So that's why the R is here, all right? So, RL, e to the minus t, R divided by L, RC, e to the minus t divided by RC, right? LC, store energy, L and C store energy. Oops. Bigger, slower. Right? More mass means it's going to take more to get going. Right? A bigger bucket means it's going to take longer to fill the bucket up. Right? R, RC, bigger, slower filling bucket. So you get that. R, RL, bigger, slows speed faster, e to the minus t, R divided by L. All right. Or you say, all right, e to the minus t divided by c, e to the minus t divided by L. I memorized this one and memorized that the inductor's backwards, different. So, and in 110, right, we do like a really formal way of looking at it, but I think this intuitive thing really helps you understand what's going on. Especially on a job interview, they'll throw up some circuit and they'll say that you've never seen before. And they don't want you writing differential equations. They want to say, well, okay, it's starting here, and that means, the inductor's impedance at DC is 0, so a lot of current is flowing through here. But the impedance of a capacitor at DC is infinite, so no current is flowing through there. Now, as time goes on, and you just kind of have this conversation, right? That's really what they want you to be able to do. Because when you're working on a new circuit you've never seen, or a new product, or you're creating something new, right? That's how you're thinking about it. You don't say, well, I need to design a new filter. All right, let me write the differential equations. You think about it more intuitively. All right. Oh, any questions so far? All right. So to me, that's kind of like that fundamental thing right here, and we'll come back to it. Is, as I've mentioned before, for these kinds of problems, where do I start? Where do I end? How long? All right. Okay. So knowing what we know, there needs to be some kind of e to the minus t r divided by L. Now, in other problems, there's going to be resistors that are there that might slow you down or might, they may or may not be important. Now, in this case, there's one R and one L. So we know that, we just know that, right? I wouldn't on the exam start going back to fundamental principles. All right, so where do we start? All right, well, the switch is open. All current flows through R and L, and we'll just, we'll just say it, right? IR equals IL equals I naught, right? Because it's all in series. All right. Now, looking at it, they want, what we're going to be plotting is VR. All right. Because if that's there, all right. So switch is open, all current, right? Current is constant, well, this is a constant current source, and we're saying that if it's constant and doesn't change in time, that it's DC. If it's DC, the frequency is 0, and ZL equals SL. And if we substitute S equals J omega, right, and omega equals 0 radians per second, then SL equals 0. So effectively, that's a short, right, at time equals 0. All right. Remember the flywheel. This will always have resistance no matter what the frequency is. But once this comes up to speed, it doesn't take any energy to keep it going. Now, yeah, it really does, because there's hidden resistances in there, no doubt, right? But an ideal element, right, is what we're talking about. Or we can call it a superconducting inductor. All right. So that means, let's so VL at t less than 0 equals 0, and then that means all the voltage is dropping across the resistor. All right. So they're talking about, what is the equation, not through current through the inductor, but they want the relationship of the voltage across the resistor. So in fact, VR t then less than 0. And so, yeah, really, it's just I naught times R. That's where we're going to start. All right, let's end it. I'm just going to redraw it. We close the switch. All right. Now, this really is a very mathematical type of picture. All the current now is going through here. There used to be 2 nodes, but now it's actually the same node. Right? All of that's at the same potential. So this current keeps recirculating, right? Now, yeah, if you probably shorted a current source, I don't know what would happen, right? But it's a good way to ask the question without getting into how that's done. So everything's at the same potential. Well, now I can redraw the circuit. And I'm going to do it in 2 steps. Here, right? And again, this is all the same point, and that's at the same point. Current can go from here through a resistor to here, and go from this point to here through an inductor, 2 separate paths, same beginning and end, I can redraw the picture into something more familiar, right? Well, and I might have jumped the gun a little bit, but that's the next part, how long. But think about it, as I have VR, right? I have this inductor current. Now there's nothing supplying it. Eventually the current will go to 0, right? So if VR equals IR, right? VR equals 0. And I'm going to put in quotes, after long time. All right, and we'll talk about that. So where do we end? Now, yeah, maybe what's an easy way to think? If you take away the power supply, these circuits end up dissipating all their energy into 0, right? Now, if you're adding a power supply, well, no, it's going to not be 0. Or if you're adding energy to the circuit. All right. Now, yeah, I kind of jumped the gun. About how long? Sorry. I'm going to redraw this, and then I'm going to answer your question. What's your question?
When you say current will go to 0, are we talking about the current specifically in that small section of the circuit?
All right, I'm going to redraw this bigger to answer your question. And I think this probably gives people who like to feel how things work a hard time, right? IR equals IL. Oh. I try to use the capital one when I'm doing the S domain. IL. Now, you're probably thinking, hey, this is a wire, and it has, let's call it 2 centimeters. And it's on your proto board. And let's say you're being really tight. Like let's make it even like super tight. Like you've got your proto board, right? And I'm kind of drawing a physical resistor, here. And then 2 holes over, and I don't like these proto boards, by the way. And here's the thing, inductors, you can buy them and it kind of looks like a resistor. You don't have to buy something that they can be packaged where they look like a resistor. So even, let's just say it's 2 millimeters of distance and 2 millimeters of distance. So how can these currents be the same when things are changing? Right? It's things can't go faster than the speed of light, right? So how would this communicate to that? Well, mathematically, even though I've drawn this, right, or let's just say mathematically, for a nodal or mesh, right, wires have 0 R, L, and C. All right, because this would even happen if we just thought about resistance. Right, because even if I added the resistance of these wires in here, we'd still have a problem. Right, how can the current instantaneously change from one spot to another? How can they communicate faster than the speed of light? And is that mathematically this picture and this picture and are the same. All right. And so when this current is zero, that current is zero, and it happens at the same time. Even though we're storing energy here at any moment in time, the current is the same. Just like the voltage is the same from here to here as here to here. Okay. And so ideal resistors, inductors, and capacitances, yeah, they're kind of a mathematical abstraction. And these pictures are mathematical abstractions. What, so what would, but this idea like, wait, this can't be. It's going to take time for a change here to come over here. Well, from physics 51, you probably had like a wire, and you can make wires have R, L, and C, right? You might not see it easily, but Maxwell's equations, you can derive a piece of wire. Not only does it have resistance, it actually has inductance, it actually has capacitance, and I have an impedance analyzer in my office. If you want to, we can take some wires, hook them up, and it'll tell you what they are. Now, how is it that you took your circuits lab and your 98 and this never came up? Oh, because if we use frequencies that are kind of low and it doesn't we don't run into it. But that thing that you're saying, right? How did you say it? How can the current in that part of the circuit be different, or how can it be the same in this part as over here, right? And it's because it's a mathematical abstraction, and that's kind of the definition of series current. The current here is the same here, is the same here at any moment in time, right? The voltage from here to here, here to here, it's all the same. But in a physical system, right, if that was a wire, I would get slightly different measurements as I was getting different resistance values. Now, very hard to detect, but when you're doing an advanced circuit design, yeah, sometimes you'll have a wire go to one thing, and they need, like I have a wire going to from a signal from here to here, right? And that signal is actually going to this thing, but the distance is different. So sometimes you might have to make it as electrically long to balance that time of flight. Way beyond what we're talking about today. But what I really appreciate about that question is it's like a question I struggled with. And the thing is you're right. that's reality. And but what it is with these abstractions, you get the big picture of what's going on. You get answers that are fairly accurate. And when they stop being accurate, oh, well, you just make a more complex model. Oh, does that answer your question? Or was that like way off topic?
So on this half of you said the current goes to zero.
Yeah.
Does that mean the current goes to zero on this half of the circuit specifically, or because wouldn't this current go to I naught?
I'm going to rewrite your question on the. So, yeah, this current is still I naught. and it's going in a loop. But this isn't like really a resistor, because remember what I said, this is all mathematically all the same point, right? So I could redraw this to where, like, you can't draw it because I've drawn this current source two-dimensionally, right? But there's no separation between here and here. So it's like a point, and the current is inside, starts to, but let's maybe make it a little different. Let's put a resistor there. Okay. I'm going to call that R and L. And I'll call that I1. Well, now there's two paths. Some of the current will go through here. Some of the current will go through there. Depending on what's going on, as the waveform changes, as the frequency of the waveform changes, it changes this value here, right? But what if R1 goes to 0, all right? And let's just say, and I'm going to make it even simpler. R1, R2, or no, that's R1. Call it R2, R3. All right. These are a parallel combination, right? So I have R1, R2, R3, current source, right? Now, IR1 equals, and this is current division, and I'm just going to IR1 equals R2 plus R3 divided by R1 plus R2 plus R3 I naught. All right. Then the next part is IR2 equals IR3 equals R1 plus R2 plus R3 I naught. So R1 goes to 0, IR2 plus equals to IR3 would equal 0, right? And then here, R1 goes to 0, we would get, I can see you nodding your head, but let me just finish it on the, right? It all becomes that. Is that a question? Or did somebody just add? So I heard a ding. Oh, okay, sorry. All right. Anyway, usually it'll bounce up. Somebody raises their hand and has a question. So when we had this case, this R was equal to infinity. When we had this case, R equals 0. So all the current, so I naught is still going from one end of I naught to the other, right? But none of that supply current is going through these two. Now the inductor, to come back here, yeah, we've got current flowing in both loops, right? And then when this goes to 0, the switch is closed, that current is being stored in the inductor. So it doesn't go to 0 right away. That energy gets dissipated. It gets dissipated with the resistor. All right. So how long is in blue? E to the minus T R L. Now, I want to talk a little bit more about how long. And the meaning of 5 tau. So we started off at I naught R, and we exponentially decayed down to 0, and this is VR, this is time. All right. You know, how long does that take? Well, actually, we all accept that 5 tau is, you're effectively at 0. And let's just go over that. So if e to the minus t RL, right, when does that get close to 0? I'm going to make a thing where tau equals L over R. All right. So let's use 5 tau. So e to the minus, t equals 5 tau will be 5 tau divided by tau will equal e to the minus 5, which is, very close to 0. So on the skill audit, on the 101, right, it'll really want this number times t, where tau is the inverse. But on a job interview, and they say, well, how long is it going to take to get to 0? Well, effectively 5 tau, but tau is the inverse of that. All right, because RL would be like a frequency times a time, which would cancel the units. Okay. Oh. Do you guys have more time? I'm going to find that one's the inverse, right? And the RLC, that's like a separate day. We'll do that another day. Where are all my inductor problems? All right, so where do we start? Switch is open, right? This current, and they're asking about I here. All right, so all of this I comes through R1, right? It's in series, so whatever the current is here, the current is here. All right, then it splits up here and here. T less than 0. Well, right, VL equals 0 at DC. Circuit is at DC before switch. All right. So if VL equals 0 and IL not equal to 0, right, that means kind of like the impedance is 0, right? Or inductor shorted. Right. So if this is shorted, VL is 0, but the current isn't 0. Well, the only way that happens is it is a short from the impedance, right? ZL equals SC. If we set that equal to J omega and omega is SL, excuse me, then the impedance is 0. So I have a zero impedance in parallel with non-zero. All of the current is going to go through that. So it starts off there. Okay. Now, where will it end? Well, this is kind of the same thing. We close the switch, but we have this resistance and that resistance and this inductor. Oops. Let me make that more inductory, right? Well, I can redraw that again. Okay. Now I might have two resistors here, but I have whatever energy stored in that inductor will dissipate to 0. So I infinity, or IL infinity, is going to equal to 0. Now in the last problem, we then use that to say VR was equal to 0. Now, how long? Well, I have R1 and R2 and L, but notice that's really just R1 in parallel with R2. Well, if I didn't tell you it was R1 in parallel with R2, you would have just said e to the minus t R divided by L. Well, it's R effective now, right? And so in this case, right, it's e to the minus t R effective divided by L equals e to the minus t R1 parallel R2 divided by L, right? Which then you can use to figure out how long. Now, because, hey, it starts at I naught, it goes down to 0, exponential decay, right? What is the equation? Oh, the equation is I naught e to the minus t R1 parallel R2 divided by L, all right? And I should probably, all right, back here, right? What is the equation? Right? Well, it started off at I naught R. That's what exponentially decays, right? So this is the actual mathematical model that would show up in the 101. All right. Now, we're running out of time for today, but there is a problem that does this. All right. The switch closes. Well, what happens is the switch closes and it shorts this resistor. And so you really get e to the minus R2 divided by L. But when we open it, that resistor is not shorted, okay? And we're out of time. Oops, let me just put the T in here. So the current comes through here. It does go through there when it's open. And so in fact, it has a different charging up time versus the discharge time. But here's the thing, even a charging up circuit has an exponential decay. I'm just going to stop this, and if you have questions for me after, that's fine. Just let me stop. Oh, did I? All right.